Hello everyone, welcome to today's live interactive session or live discussion session on geology on soil mechanics. Uh, in the previous session, we solved some problems from the seepage topic. We solved problem related to seepage in dams. We found out the seepage flow through an earthen dam and other structures with the help of flow net, right? And we also solved some problems where we calculated the pressure head at the bottom of hydraulic structures. Is it right? So in today's session, what we are going to do, we are going to start the topic of consolidation a bit, and then we will be solving some problems based on that. Okay, so let us start the session. So before that, let us see what is capillary rise in soils. So the continuous voids present in soil can behave as capillary tubes. So continuous. So the soil mass, as you know, is made up of what? The pore structure. Okay, there are the soil grains, and then you have the pore structure, and this interconnected pores somehow behave such like a capillary tube. All right. So what happens? So when you have a glass of water or a glass of cold drink and you put your straw into the cold drink, what happens? The cold drink rises up automatically through the tube or through the straw a bit, right? It rises up the straw a bit. So this action or this property is known as the capillarity. Right, so due to surface tension of water, the water in this tube rises above the phreatic surface. So see if this is the straw and this is my water surface. So as soon as you dip the straw into the water is going to rise up. In inside the straw, the water is going to rise up, say up to this level, a higher level than the phreatic surface. Right, so this property is also seen in case of soil, where the interconnected pore network actually behaves as a capillary tube. Now, this height by which the water rises in the straw or in the soil, that height is given by this HC, the capillary height, and this height is given by HC, which is nothing but equal to 4T cos alpha by D gamma W. Okay, 4T cos alpha by D gamma W. Right? So for pure water in clean glass, alpha is equal to 0. You can have HC is equal to 4T by D gamma W. Okay. Now in case of soil, this rise of height of capillary rise, okay, this rise of water, the height by which the water rises, this height of capillary is given by this, where H is equal to C by ET10. Okay, the C is nothing but this C is a constant. Okay, you know is the void ratio, and this is nothing but the D10 size or the what or the effective size. Okay, effective size of the sample. Okay, this is the height. Okay, this is the water level. Okay, this is the height by which this capillarity, the capillary will rise. Okay. Then we solved some problems in the previous session also using this. So in the zone of capillarity, so say so this is the water level and the water rises to this level. Okay, due to capillarity. Okay, at this level, if I want to find out the effective stress, if I want to find out the effective stress, so effective stress is what? Total stress minus pore water pressure. So here the pore water pressure is actually negative minus H into gamma W, HC into gamma W, or H into gamma W. It's nothing but the height of capillary rise. Finally, it becomes H C into gamma W. Okay. In case of partial saturation, okay, if the soil after capillary rise, that part of the soil is not completely saturated, then this U is given by this. Okay, where S is the percentage saturation of the soil. In that part, the S by 100, H into gamma. Now let us see consolidation. Okay, so what is consolidation? Now you have a soil mass, that completely saturated soil mass. Now, as soon as you apply some loading onto the soil, as soon as you apply some loading into the soil, it may be some in the what to say, maybe in form of some surcharge or some external loading. Okay, as soon as you apply that external loading into the soil, at the instant you apply the load, there is going to be some elastic settlement. Okay, elastic settlement that occurs immediately as soon as you apply the stress or apply the load to the soil. There is going to be elastic settlement. This elastic settlement due to increase in the stress in the saturated clay layer. What is going to happen? As soon as you apply the load, there is going to be increase in the saturated clay layer, and elastic settlement is going to happen, right? So initially, as soon as you apply the load, first immediately this elastic settlement will occur. So this elastic settlement is known as the immediate settlement. Okay, this is also known as the immediate settlement. Now, in clay soil, what happens if the clay soil is completely saturated? You already know that the clay has very low hydraulic conductivity, right? The clay has very low hydraulic conductivity, or that is the clay soil have very less what? Very less permeability. So what happens when you apply the load? There is a tendency that the water wants to. So if you say consider a sponge. Okay, sponge, you have a sponge, a foam sponge. You might have seen sponge, right? So you dip the sponge in a soil, so dip the sponge in water, so it becomes completely saturated with water, and now keep it in the table. Now, as soon as you apply pressure with your hand, what happens? The water comes out from the sponge, right? So the same thing happens in case of water, the case of clay soil, right? As soon as we apply some load or pressure into the soil, the water will want to come out of the soil. But what happens? This, as you know, the hydraulic conductivity of the clay is very less. When you have a clay layer, the hydraulic conductivity is very less, right? So when you apply the load into a saturated clay layer, water slowly comes out of the soil. This water slowly comes out of the soil. So what happens as soon as we apply the load, the extra load that we're applying, that generates a excess pore water pressure. That generates a excess pore water pressure. Okay, so we apply that load. That load initially immediately generates an excess pore water pressure. Now when this excess pore water pressure is generated, right, now water takes time to flow out of the soil. So slowly what will happen? Slowly the water will come out of the soil through the drainage layers. Okay, the water will slowly come out of the clay layer through the drainage layer, and the excess pore water pressure that that had arisen, that excess pore water pressure is going to slowly get dissipated. Okay, excess pore water pressure is going to slowly get dissipated. Now this dissipation of the excess pore water pressure is accompanied by volume change of the soil. Okay, right? Or volume change means what? So obviously you're pressurizing the soil, right? So when you're pressurizing the soil, water will come out, and the height of the or the thickness of the soil is going to increase, or the volume is going to change. Volume is going to change, right? The thickness of the soil layer is going to reduce, and the volume is going to change. Okay, the volume is going to reduce. So this process of reduction of volume of the soil on application of load, or reduction in volume of clay soil on application load to be specific, followed by the dissipation of, okay, accompanied by the dissipation of excess pore water pressure, is known as consolidation. The consolidation continues. So as you know, as I said, water flows very slowly through the soil because the hydraulic conductivity is very less of clay soil. For clay soil, the hydraulic conductivity is very less. So it will take time for the excess pore water pressure to get completely dissipated. As a result of which, this volume change also is very slow. Volume change also takes time. So this is known as consolidation. It takes long time. Okay, after the immediate settlement, after the immediate settlement, this consolidation settlement or consolidation volume change takes a lot of time. Okay, so this is the process of consolidation. Now let us see the spring cylinder model to better visualize the consolidation process. Now a saturated clay soil can be what? A saturated clay soil can be represented by this, right? So you have a piston, okay, you have a cylinder, okay, this cylinder, you have a spring, okay, and here you have valves, okay, and this is completely saturated. So initially the valve is closed. Now, as soon as you apply some load here, see, you have applied some load into the spring, right? So as soon as we apply some load into the spring, what is going to happen? This load will get immediately transferred to the, okay, so here you have a piston kind of thing, okay, and then inside you have springs, okay, and then you are applying it. So as soon as we apply the load, what is going, that load will get immediately transferred as load will immediately appear as the excess pore water pressure. Okay, this load, whatever load we are applying, this load will immediately get transformed to the excess pore water pressure. You can see the excess pore water increased by equal amount. Right. Now, see the valve is closed. Now, as soon as you open the valve, what will happen? Slowly, slowly, water will start coming out from here. Water will start to come from the valve as you open the valve. So as you open the valve, water uh, tries to come out, and the pore water pressure keeps on reducing. Pore water pressure keeps on reducing, and finally, after some time, what will happen? The complete water will come out, and the pore water pressure will get reduced to zero. Excess pore water pressure will get reduced to zero. The complete load will be then transferred to the springs. That means this complete load will be now taken by the grain to grain contact of the soil. That is, the complete load is now taken by the will be seen as the effective stress of the soil, because it's taken by the grain to grain contact of the soil particle. Okay. Okay, so as soon as you apply, so first this is the case. So as soon as you apply the load, the whole load is taken by the water. Okay, P by A, excess pore water pressure. So the excess pore water pressure increases to this value. When you open the valve, slowly the excess pore water pressure keeps on reducing. The load gets transferred from the water to the soil structure. Okay, so the soil structure. Because that is the effective stress has to increase. Now gradually what will happen at this level? All the excess pore water pressure will get dissipated, and my effective stress will now be equal to P by A. Okay. Well, let us see this arrangement here. So you have sand layer at the top. Okay, this is the sand layer. This complete is the sand layer, and bottom also you have a sand layer. The sand layer sandwiches. So this clay layer is sandwiched between two sand layers, one at the top, one at the bottom. This clay layer is sandwiched between two sand layers. Okay, the clay layer is sandwiched between two sand layers. Now, capital H is the thickness of the clay layer. Okay, and you have the groundwater level here. That means my clay is fully saturated. The clay is fully saturated. Okay, clay is fully saturated. But as soon as we apply some external load, this load will get generated as the pore water pressure in this clay layer. Okay, it will increase the pore water pressure in this clay layer. Now, as time passes, the water will get drained out in these two sides, these two faces to the sand layer, and in these two directions, top and bottom, the excess pore water will get the pore water will get dissipated. So the excess pore water pressure is going to slowly reduce. Okay, and what will happen due to that? The settlement of this clay layer will be occurring. So let us see this. Okay. So here you see at time t is equal to 0. Sorry. So at time t is equal to 0, at time t is equal to 0, as soon as we apply this load, as soon as we apply this load, you are seeing that what? You are seeing that the pore water pressure is equal to that applied stress. The pore water pressure gets equal to that stress. Isn't it right? Right? Delta U is equal to delta sigma. Right? And the effective stress is 0 because all the that external load, whatever you applied the vertical load that you applied, the vertical stress that you applied, that vertical stress is directly immediately taken by the water. Okay, it is not yet transferred to the soil structure. That is why the effective stress is 0. Now what happens? Now gradually what happens? At time just beyond time t is equal to 0, just beyond time t equal to 0. Okay, what is going to happen immediately at the top and bottom at this and this phases, this phase, the pore water pressure will immediately become 0. The excess pore water pressure will immediately become 0 because it are drainage phases, right? These are drainage phases. So the water molecule here will immediately get dissipated out. So here the pore water pressure becomes excess pore water pressure becomes immediately 0. And at the center you are seeing a maximum pore water pressure. So at any time t, what will happen? The pore water pressure is going to get reduced. So initially it was delta sigma, now it will get reduced. Okay, and this is how the pore water pressure distribution is going to be there, right? And whatever the effective stress at the top and bottom, the effective stress is going to be the maximum, which is nothing but the delta sigma. And at the center here at the middle, the effective stress is going to be the minimum because the excess pore water pressure is maximum there. Right? Now, at time t is equal to infinity, when the all the excess pore water pressure has been dissipated. Right? So at time t is equal to infinity, when all the excess pore water pressure is dissipated, at that time what will happen? See, water pressure is 0, and now along the whole soil layer, the complete depth, my effective stress is now equal to the applied stress. Right? The pore water pressure becomes 0. And when this happens, there will be some consolidation settlement. There will be some consolidation settlement in this process of this criteria. Okay. So now there is a test called the one-dimensional consolidation test. Okay, what we do in this test, we plot. We generally our target is to plot the void ratio versus the effective stress curve. Okay, we plot the void ratio versus the log of effective stress curve we plot from this. Also, we can plot the time. Okay, the time and the deformation. The deformation in the y and the time in the x. That's what also we can make with the help of this test. This is the one-dimensional consolidation test. So from this test, we can determine the parameters. That is the coefficient of consolidation. Okay, the all this stuff we'll see that in the next slide. All these parameters we actually determine, which helps us to calculate how much amount the soil is going to settle due to this consolidation phenomenon. Okay, this consolidation phenomenon, by how much amount that clay layer is going to settle. Always remember that consolidation is something that is seen only in clay soil. For sandy soil, this immediately drainage happens, right? So there's always immediate settlement only. There is no consolidation settlement because immediately the pore water pressure dissipates out in sandy soil where there is easy drainage through the pores. Very variability. So there is easy drainage out. This is generally seen only in the clay layers, clay soil. So this is the consolidation test. So we put the soil specimen here, and then we have the porous stone that is kept. Okay, and this is the specimen ring inside which we put the soil specimen. So please go through the textbooks, standard textbooks. In there, everything is given in detail. Okay. Then we apply the load and we take the dial gauge reading. Okay, dial gauge reading. So we put, say, first we put point zero point 0.5 kilograms, and then keep on noting the dial gauge reading till, say, 24 hours in equal intervals. We keep on, then we keep on noting down the reading. Then we again increase the load, and then we again take on the reading. Okay, so like this we take the to see the videos. You will get many videos over the internet of, for one dimensional consolidation test. So please see those videos and read some textbooks also. Okay, and obviously, if you are in your bachelor's level, obviously you will be doing this in your soil mechanics or geotechnical engineering laboratory course. Okay, at that time everything will be mostly how to do this test. Okay? The specimen size is this 64 diameter of the soil specimen, circular specimen, and 25 millimeter thick. Load is applied to the specimen submerged underwater. That is, we keep the specimen fully saturated. But always remember this, we keep the sample fully saturated. Each load is usually kept for 24 hours. As I said, we keep the load and we note down the settlement, keep noting down the settlement at equal interval of self time. So at 1 minute, then 2 minutes, then 4 minutes, then 8 minutes, then 16 minutes, then 32 minutes, then like this 64 minutes, then like this, we keep on noting down at equal, like we keep on noting down the settlement for at least 24 hours. And then the load is doubled. So initially, say if we put 500 grams and we make it 1000 grams, like that, you double the load. And you carry on the test. Okay, it's a long test, so it takes several days to complete. Okay, it takes several days to complete. Now for each uh, each loading, you will get a curve something like this. Okay, you have the deformation and the time in the log scale here. So as soon as you load the sample, there is going to be some initial compression. Okay, this is the first stage. Immediately, whatever compression of the soil structure happens, immediately re-engagement of the soil structure will happen. That gives a result to the initial compression. Then you have a long period of this primary consolidation stage. Okay, primary consolidation, and at the end you have settle some more consolidation that happens with the plastic readjustment of the soil. That is known as the secondary consolidation. So you have the initial compression caused by the preloading, then you have the primary consolidation, and then you have the secondary consolidation caused by plastic adjustment of the soil. Now, we to construct the void ratio pressure process. I said E versus log P. Void ratio versus pressure, log of pressure. Okay, we plot this. In order to generate this E versus log P curves, we use this height of the sample method to find out the void ratio. Let us see how. So first we calculate the height of soil solids. So what is the height of soil solids? Height. So volume of soil solids is what? Volume of soil solids is weight of soil solids divided by G gamma W. Right. So we can have this, right? So height of soil solids times area is nothing but my volume of soil solids, right? Now volume of, right, isn't it? Isn't it? So from there I can write it like this, and now weight I can also write in terms of mass. If I write in terms of gamma W instead of unit weight, I'm writing in terms of density. I can write it like this, right? So I can get the height of soil solid. So I know the weight of the soil, I know the density of this water. I know GS, the specific gravity of soil solids. I know the area of cross section of the soil sample. I can find out the height of soil solids, right? Height of soil solid, height of solids. I can find out. Okay, then you have the initial height of voids. So initial height of voids is equal to total height minus height. So in terms of volume, you already know, right? So you have the volume of soils, solids, then here we have the volume of voids, right? So the and if you have the total volume, so total volume is equal to volume of the volume of voids equal to total volume minus volume of solids, right? So similarly, we can write in terms of height like this. Okay. How to calculate the void ratio? Void ratio is nothing but volume of voids by volume of solids, nothing but HV by HS. Okay, so we got the initial void ratio. Next, for the first incremental loading, the change in void ratio is going to be delta H1 by HS. Delta H1 by HS. Now for the new void ratio, we have the void ratio is going to increase. The void ratio is going to decrease. So E1 now is equal to E naught minus delta EI. Similarly, E2 is equal to E1 minus delta H2 by HS. So like this, we will continue to solve. We will solve our problem, then it will be more clear. Okay. So as we keep on increasing the load, the void ratio is going to reduce. So that void ratio, this way we are going to calculate it. Okay, this way we are going to calculate. Okay. And there is one more method in which you can do, that is known as the change in void ratio method. So how to do that? So the specimen is assumed to be completely saturated at the end of the test. Okay. Now at the end of the test, we can find out the final void ratio is equal to W into G. S is 1. S is 1. The final void ratio is equal to water content at the end of the test times the G, specific gravity. So EF is equal to WF into G. After that, we find out EF, then we can calculate. So we know delta H by H equal to delta E by 1 plus E naught. Okay. And the void ratio at the end of effective stress is going to be this. And this delta values can be found out from this. Okay. So like this, we calculate the this thing. Okay. So again, see here, delta V by V, the change in volume is nothing but delta E by 1 plus E naught. Okay. So from there, we get this. Okay. E is what? Volume of voids by volume of solids. Right. So from there, only this thing is derived. Okay. Okay. So you get this delta E. The delta E here, the delta is nothing but this. Okay. Now there are two types of soil you can normally consolidated and over consolidated soil. Okay, normally consolidated soil and over consolidated soil, and this is determined by the over consolidation ratio. Say you have a soil, okay, you have a soil. You first apply 50 kilo for 50 uh, 50 pascal load in it, then you increase to 50 kilopascals, 100 kilopascals, then you increase the loading on the soil to 150 kilopascals, right? So 150 kilopascals is the maximum load that has been taken by the soil. Now you reduce the loading to 100 kilopascal again. Now that state of the soil, that state of the soil is known as the over consolidated state, because initially you had loaded it to a higher value, but now presently the load which the soil is taking is not that much. So that will be the over consolidated state. Okay, you can see max applied stress in the past was 150 kPa and present applied effective stress is 100 kPa. So the OCR value is greater than 1. So hence we call this type of soil as over consolidated soil. And now for normally consolidated soil, whatever load you are applying presently, that is only the maximum, that is only the maximum stress that it has taken, right? Okay, so if a virgin soil, you are applying the load. If a virgin soil, you are applying the load. So first you apply 50, then 100, 150, then 200. Now 200 is the maximum that soil that is taken. The max stress applied in the past is 200 and present applied stress is also. This is only that one present is also the parts of the soil. Normally consider the OCR is to be 1. Okay, so that is known as the over consolidated state of the soil. Okay. Oh, I spoke about some parameters, right? So see, so when you have you plot the E versus uh, effective stress plot. So your word ratio versus effective stress, also word ratio versus log of effective stress. Okay, two types actually. Now for normally consolidated, the curve is going to be something like this. Okay, this is for normally consolidated. Okay, this is for normally consolidated. And for over consolidated soil, the curve is going to be something like this. And this is going to be over consolidated. Okay, this is how the curves are going to look for normally consolidated and over consolidated. Okay. Now, what is coefficient of compressibility? Coefficient of compressibility is nothing but the slope of E versus effective stress curve. This is nothing but our coefficient of compressibility. So remember these things. So for all these parameters, we have to remember. What is coefficient of compressibility? The coefficient of compressibility is nothing but the slope of the E versus what? E void ratio versus the effective stress plot. Now, what is compression index? Compression index is the slope of the E versus log of effective stress plot. Okay, this is nothing but the compression index. Coefficient of volume change MV is nothing but AB by 1 plus E naught. Okay. Swelling index. Swelling index is so we'll see what swelling index is and now what recompression index is. So all these things we'll see in the next slide. Okay, let us see. Now, so here you have your okay, so here you have E, you have log of effective stress. Now, initially you have a virgin soil, right? You have a virgin soil initially. Now what you do? So say our soil was first over consolidated till a point of this. Say our soil was over consolidated due to at this stress level first. So at up to this stress level, our soil is over consolidated. Like before you had loaded to this part, that soil had encountered a load up to this part, this stress level. So our soil will be called as over consolidated. Now as you increase the load from the zero value, our curve will be like this. Because up to this point our soil is over consolidated. Okay, this part is soil is over consolidated to this part, and this is my initial word ratio. Not inert is the over consolidation ratio. Now next what is going to happen, as soon as you cross this line, this line marks the boundary of the over consolidated state and the normally consolidated state. Because now whatever the stress the soil is going to take after this barrier, whatever the stress the soil is going to take, that is the maximum soil stress that the soil is encountered at that point. It is a normally consolidated state. It's going to behave as a normally consolidated state. So our curve is going to come something like this now. Okay. So this one is the virgin curve. Virgin. Now you if you unload the soil, if you unload the soil completely, the soil is going to come to have something like this. To a void ratio E1. So you cannot go back to E0 because there will be some plastic deformation in the soil. You will reach a void ratio of V1. This is the expansion curve. And then if you recompress it again, it will be something like this again. Okay. Now this state is also the normal. And this pressure is known as the pre-consolidation stress. So this pressure is known as the pre-consolidation stress. Now let us see. Now the swelling index is nothing but the slope of that swelling curve. Okay, expansion curve. Decompression index is the slope of the decompression. Okay. Just a second, huh? Just a moment. Next, we are done with the summary. We'll just solve the problems next. Just see something. So let us see this problem. Compute the maximum capillarity tension for a tube of 0.12 mm in diameter at 4 degrees Celsius. So how can we do that? So for tube H, I can write as 0.308. What is the constant C divided by E diameter? Now what is 0.3084 to or therefore part. Okay. Now let's see. The capillary rise in a soil having the effective size as 0.07 mm is 49 centimeter. Estimate the capillary rise in another soil having its effective size as 0.12 millimeter. Assume same wide ratios in both soil. Now you know the height of capillary soil in the height of capillary rise in a soil is given by this E into D10. Now we can say this H times D10 is equal to a constant. Okay, because void ratio is same and C is a constant for this type of soil. So for same type of soil and same void ratio, or C by E is going to be a constant with nothing but H into D naught D10. So we can have 49 into 0.07 is equal to H times 0.12. From here I can get. So you can see if our size increases, if the diameter size or diameter of void, okay, if the D10 size, effective size increases, what is going to happen? The pore size also is going to increase the capillarity, that pore network, that the diameter of the pore network is going to get increased. right? So with that, what happens? The height, the capillary height will also increase. Okay. Let us see this. This is a problem from the consolidation test. Okay, this is a problem from the consolidation test. The following observations are recorded in a consolidation test. Initial height of specimen is 20 millimeters. Dia of specimen is 75 millimeters. And the specific gravity of soil solids is 2.77 and 2.77. And the final water content is 39%. Final water content at the end of the test, the final water content of the soil sample, that is 39%. Applied water pressure is given, applied pressure is given, and the final gauge reading is given. Calculate void ratio corresponding to each pressure increment. So the gauge reading correspond at the end of each loading. At the end of each loading, the reading of the strain gauge is given along with the that pressure, corresponding pressure. Okay, applied pressure. We need to calculate the void ratio corresponding to each pressure. So obviously we want to put the void ratio versus pressure curve. So we need to do this. Right. So we'll be using the void ratio, the final void ratio, right? We will use this method. We will use this change in void ratio method to calculate the void ratio corresponding to each loaded level. Okay. So you have equal to final water content times the GS. So final water content is 0.39. This 39% is given to us, and G is 2.77. So you get 1.08. 1.08 is my final void ratio. Right? Now, initial height of specimen is 20 mm. Okay, initial height of 20 mm. And at the end of the test, what is our gauge reading? 766. Okay, 766 is the at the end. At the end, that was the gauge reading. And initially at zero loading, initial at the test, we had the gauge reading of 100. Because the total change in height that is undergone by the soil is 766 minus 100. The change in height that is the soil has undergone 766 minus 100 into 20 minus 2 into 6.66 mm. So this much change in height the soil, initial height of the soil at the start of the sample to the at the end of the sample, what is the height? That difference, that this much difference in the height we have got. Therefore, final height, if initial height was 20, the final height is going to be 20 minus 6.66. It is 13.34 mm. This is our nothing but the final height of specimen, isn't it? Now delta E is what? Delta H by H final height by 1 plus E final equal to delta H 1 plus 1.08 by 13.34. Okay, it's equal to 0.156 times delta H. Okay, this is my change in void ratio, and this delta H is in mm. Okay, now let us see how to do. So for this, what we will be doing is that we will be making one table. So So first we have the applied pressure, then we have the dial gauge reading, then we have our delta H in mm, then we have H in mm, then you have delta E. What is delta E? Delta E is nothing but 0.156 times 0.156 times that delta H. 0.156 delta H. And then we have the void ratio, that is E final minus delta E. Okay, we'll start from bottom. We'll see that. Okay. 0, 50, 100, 200, 400, 800, 0. Okay, to make so now see dial gauge reading at the end. Let us write down. Okay, all the dial gauge readings. Now, what is my delta H? Delta H at the where did it go? Yeah, just a second. Huh? So I have my E final. I already calculated 1.08. Okay, and delta E 0.156. The calculator. Yeah, yeah. Just give me a second. Huh? Because I also am doing with you only. It's not solved. 1.08 6 times. Huh. So final height was 13.4, 13.34, right? So I will write the final height here, 13.34. Okay, and by how much the height reduced? Hmm. 13.34 and 766 minus 8.766 minus 899. You'll get 133. So 1.33. This 1.33. So 134. So from here to what? 899 to 766. How much means from 766 to 899? How much change? Okay, that I'm calculating. So 134. My change is this much. Okay, so how much will be this thing? This will be 113.34 minus 1.33. Because higher load height should be less, so it will be 12.01. 12.01. Okay, like this we have to do. And similarly here 1.08 is the void ratio here. 1.08 is the void ratio here. And what is my change in void ratio? 0.156 times delta H. What is my delta H? 1.33. 1.33 if I multiply 0.207. 0.207. So this minus this will give me this. It is nothing but 1.08 minus 0.207, nothing but 0.873. Okay. Now again here equal to 899, or sorry, minus 760. So 899 minus 768. 899 minus 768 is 131. That means that will be minus. Okay, now I will have minus 0.31. This is going to be 12.01, 12.01 plus 1.31, 13.32. Similarly, 0.873, 873, right? And then we have 1.31 times 0.156. Give you 0.204 minus. It will be minus 0.204. So from here, I will go to here. Nothing but 0.873 minus of minus 0.204. This is plus 0.204 will give me 1.077. Okay, understood, right? So like this, we need to proceed. Again, here I will have 632 minus 768, 136, that is minus 1.36. And here then I have 0.156 times 1.36 is 0.212. This 13.32 plus 1.6, 14.68 is going to 1.077 plus 0.212, 0.289. Okay, like this we have to go. Again, for 499 minus 632, 499 minus 632 will be 133, means minus 1.33. Get it? 152. 33, right? 33. So this one will be 14.68 plus 133, 16.01. And 1.33 times 1.156 will be minus 0.207 plus 1.496. Similarly, here I will have minus 1.40. Here I will have minus 0.218. So this if I do 17.41, and here I will have 7.4. All right, now this minus this, I will have again minus 2.59, and this if I do minus 0.404, this 2.118, this if I do like 20. Isn't it? Right? So initially we started from so backwards we did from down bottom to top. Okay. So initial void ratio like this if you plot now, initial pressure, initial void ratio is what? 2.118. Then it keeps on reducing, and then you unload it again, it comes something like here. So like this you got some. Okay, so this way you need to do. Okay, this way you need to solve the problem one by one. So initially you get this relation, this is this relation you got. This relation you keep on using for each individual delta H's to calculate the everything, and you get first final E and the final height you calculate first, and from there you proceed backwards to the top. Okay, so this way you need to do. Now let us see one. The following observations are recorded in a consolidation test, each load being maintained for 24 hours. The specific gravity of soil solids is 2.72 and the final water content is 28%. Alright, the applied pressure is given and the sample thickness is given. Okay, again we need to calculate the void ratio at the end of each. Similar to the previous problem. Okay, so here again final water content is given, and yeah, so let us see how to do this. So we have final void ratio. Just a second. So we have delta H by right. So here we are calculating this 18.36 minus 18.990. This thing we are calculating here for these two. We'll get delta E by 1 plus the delta E is E1 is equal to EF plus delta E, isn't it? So because E1 is here, okay, means the void ratio is going to reduce here. So we have 0.762 minus 0.712. So here at this part, the void ratio is 0.712. Similarly, again, if you do 6, so 18.36 and this thing happening. 18.36. We're just using this relation we are trying to find out of. Just for two pairs we are doing. Okay. And have type 2 is equal to and like this we can proceed. Okay. Okay, just we are using this relation delta E by 1, delta H by 1, delta H by H is equal to delta E by 1 plus E. So this relation you are using, you are finding out. Let us make the table again, we'll see. Distress H H we will see this out. Okay, first was 0, 50, 100, 200, 400, 800, 0. Okay. So this heights also we know at each level the height is given. All the heights are given. Let us write that down. Thickness is already given here. Okay, and the final void ratio calculated, it was 0.7 to 0.762, 0.50, and this is delta H plus 0.45. Right. Now again you will go backwards. Again you will go backwards. So here what we calculated 0.712. Okay, and what was the right? Let's write down the height differences first. So these height differences minus 0.20. These height differences minus 0.29. 5, 4. Okay, the height differences I just wrote down. Now delta H I got delta H by what? Delta H by what? Delta H by H is equal to delta E by 1 plus this relation I am going to use. For that, my delta E for this comes out as 0 minus 0.019. Okay, the next one 0 minus 0.019. So from here to here, if I do, we'll get 0.731. Similarly, if you find out this will be minus 0.027, will be 0.758. Then again, here I will get minus 0.028. From here I will get 0.786. Get minus 0.014. Here I will get 0.800. Then I will get minus 0.035. And I will get 0.83. Okay, from bottom to top again. Understood, right? Just you are using this relation everywhere. Delta H by is equal to delta E by 1 plus C. Okay, this 0.019 I showed here how to calculate. Now 0.027 how will we calculate? 18.85 minus 18.56. Okay, 18.85 minus 18.56 divided by 18.56 by delta E by 1 plus 0.731. You will get delta E as 0.027. Similarly, next 19.15 minus 18.85 divided by 18.85 equal to delta E by 1 plus 0.758 is equal to delta E is equal to how much? 0.028. Like this we have to do. Okay, like this you have to do for other examples. I hope it is clear to you. It's not, it's very easy. Okay, so it is that you have to back calculate that stuff. Okay, okay. So the trick is next minus present by present equal to delta E by 1 plus E of present. What is your present? And where to write this down? Where to write this down? In the present box only. Okay, in the present box only. Okay, See 18.85, 0.28. So 18.8, this 0.28 I am writing with 18.5 only. This write this delta in the present box of this present value only. Okay, like this to preview the code. Next, in a consolidation test, the void ratio of the specimen, which was 1.052 under the effective pressure of 207 kilonewton per meter square, changed to 0.932 when the pressure was increased to 430 kilonewton per meter square. Calculate the coefficient of compressibility, compression index, coefficient of volume compressibility. So change in void ratio is given. From one void ratio it reduces to another void ratio when you increase the effective pressure. Right, when the effective pressure increases from some value to the other. Okay, now you need to calculate the coefficient of compressibility, compression index, coefficient of volume compressibility. Now, what is coefficient of compressibility? The coefficient of compressibility is AV, is nothing but the slope of the void ratio versus the effective or the pressure curve, right? Now, therefore, is AV pi by 1.052 minus 0.932. What's the value I'm writing? Ignoring the sign. Will be 5.38 into 10 to the power minus 4. What is the unit? Meter square by kilonewton. E is no unit, void ratio is no unit, right? It's a ratio. And the stress units, inverse of the stress unit is meter square per unit. Now, compression index, the slope of the E versus log of stress curve, right? So delta E by log of 2 theta 1 5 2 minus 0. 0.37. Okay, next we have the coefficient of volume compressibility. The coefficient of volume compressibility is AB by 1 plus E naught. So now why this MB is known as the coefficient of volume compressibility? The coefficient of volume compressibility is nothing but the rate of change of volume by with respect to origin volume divided by the change in effective stress. So this top I can write delta H by H, isn't it? This one. Now delta H by H I can write by, isn't it? Now delta E by delta sigma bar is nothing but AV. And that's right, and which we get. This is the actual definition of coefficient of volume compressibility. For a flexible foundation with two sides, 2 meter and 3 meter, that is rectangular flexible foundation, 2 meter by 3 meters, and an axial load of 750 kilonewton, determine the elastic settlement under one of the corners. The soil has a Poisson's ratio in Young's formulas is 0.37 and 9.8 MPa respectively. Use IT as 0.70. Now, this IF, this is actually IF. Okay, IF, whatever I wanted. So, the immediate settlement, okay, immediate settlement or the elastic settlement is given by is equal to QB 1 minus mu square by PS into IF, where Q is my 750 by and 2, 3 into 2, okay, it is 125 kilonewton per meter square. This IF, so if you have a flexible foundation, right, so it's gonna deform something like this. It will be different at the corner, different at the bottom. Yeah, it's not a rigid settlement, it's going to be flexible. different at the corners, different at the middle. So this IF equal to 7.2 will give you the settlement in the one corner. Okay. So it is nothing but 125 times 2 width times 1 minus 0.37 square times 9.8 into 10 to the minus into about 3 kPa times 0.6. We'll get this as 15.4. Is it 15.4? Okay. A standard soil has a compression index of 0.28. Its void ratio at a stress of 12 kPa is 2.05 and its permeability is 3.5 into 10 to the power minus 7 mm per second. Compute the change in void ratio. The stress is increased to 21.6 kilonewton per meter square. The settlement in the above case if the soil settlement is and the settlement if the soil settlement is 6 meter. So you need to find out two things. One is the what? The void ratio, change in void ratio of the increase due to the increase in stress. And the other thing you need to find out is the settlement, the concentration settlement, and the thickness of the stratum is 6 meter. Okay, so try to do this. I will just be back in a minute. Just try. Okay, sorry for the interruption. Let us continue. So we have a soil, standard soil as a compression index. The compression index of the soil is given. Void ratio is given. Okay, void ratio is given at initial stress. So when we increase the stress, what is the changed void ratio that you need to find out, and also need to calculate the settlement. The thickness of the soil strata is given to us. Let's see how we can. So let us find the coefficient of compression index. So compression index is what? Delta E by log 10. Right? We have 0.28. It's given. It will come out as 0.07. E2 is E1 minus delta E. So E1 was thanks. Now it's also asked compute the settlement. Okay, now see delta H by H is delta E by 1 plus E naught. So this delta E I can write. So from this relation I can write delta E is Cc times log 10 1 times 1 plus E naught. So delta H is nothing but the settlement is equal to H into Cc 1 plus E naught log. Right. So you can also write this as initial height Cc initial void ratio 10 initial plus the change by initial. Okay, therefore strata thickness is this one is given to us. Now this E naught is the initial void ratio. Now initial void ratio if you want to find it like this minus it is a empirical relation. Okay, this is equal to 0.54 E naught minus 0.35 from here. To 0.8669 0.6 by 12 0.229 meter is equal to 22.9 centimeter. So this one is the settlement. Okay, what is the settlement of the soil? For the given soil profile, calculate the settlement due to primary consolidation for the 6-meter clay layer due to a surcharge of 100 kp. So try to calculate this similar to the previous problem. Try to calculate this. It's same. Okay, just try. Then I will do. Okay, do this. Try for some time. If you're not able, I will be able. I will solve it. Obviously, just try yourself how to do same. It's the concept is same to the previous problem. Okay, exactly same to whatever we solved just now. Do it. So for this, what we need to do first, is that we need to calculate the effective stresses. Effective stress, and also we need to calculate the density. So densities are not given. Okay, density are not given. So whatever we did the stresses in soils, whatever we discussed, that thing we have to do. Okay, first you need to calculate the initial effective stress. The initial effective stress at the center of this clay layer. The initial effective stress. Okay, initial stress. What was there? That we need to calculate. The change in the effective stress is given. Externally applied load surcharge of 100 Newton per meter square. This is given to you. But initially the soil, how much effective stress was. So that we need to find out first. So for that we need the densities. So first you calculate the dry density of the sand. So what? G gamma W by 1 plus E. 2.66 times it 1 to 15.17 per meter. Now clay 10 point. So for clay saturated is given. So I just find out the submerged. Okay. So now I can find out the initial effective stress. What will it be? 4 times the dry unit weight of sand plus 3 times the submerged unit weight of clay. That will directly give me the effective stress. I don't need to find out separately total stress for 100% and deduct it. Don't need. Right? Directly we can do it like this. So this will be square. Now, right? Now we have all the stuff that we need. Almost we have all the stuff. Just one thing remains. That is the CC. Also, CC will be using this relation. If I know the liquid limit, then I can find the CC. This is also one more empirical relation. Then, okay. So I will get from here. So how much is it? 89.38 plus 10 by 89.38. Right? Right? That's 0.463. That. Okay. Very simple. So the main thing is first you need to calculate the initial effective stress. Then initial effective stress, the change increase the effective stress given. Then you do the other stuff, same to the previous problem. Okay, very simple. Okay, very simple, right? Nothing much to worry about. So in a consolidation test, a thickness of saturated specimen of clay under consolidation pressure of 100 kPa is 25 mm and its water content is 15%. So let us see, understand slowly what it's given. Under a consolidation pressure of 100 kPa, a thickness of a clay specimen in a consolidation test. So we so how we do the consolidation test, right? So in during the test, the thickness of the specimen is 25 mm at a pressure of 100 kPa. The water content is 15%. Okay, 25 mm thickness specimen at 100 kPa pressure and water content 15%. On increasing the water consolidation pressure to 200 kPa, so from 100 you are increasing the pressure to 200 kPa. So what is going to happen? Specimen thickness is going to reduce. The specimen thickness reduces to 23.5 mm after consolidation. right? So as you increase the pressure, the consolidation thickness is going to, the thickness of the soil specimen is going to reduce after the consolidation. If the specific gravity of the clay is 2.7, find the compression index of the clay. If the specific gravity of the clay is 2.7, find the compression index. This is the CC we need to find out, right? Let us see how we can proceed. Very easy, very, very easy. So, EI have W into G, right? So what is W? 0.15 times G is 2.7. So this will give me the void ratio of 0.405. Now, the settlement, how much is the settlement? 1.5 mm. Okay, 1.5 mm. So I will use our settlement equation. 25. 25 mm is the height of the section. 1 plus E naught. E naught was 0.405. Right? Into log. So what is the increased stress? 200. Initially it was 100. From this we can find out what? We can find out CC. So please calculate CC from here. Please calculate CC from here. Please calculate. So CC comes out as how much? CC comes out as 0.2. Okay, 0.28. Let's go to the next problem. Yeah. A clay soil is tested in a consolidometer. That is nothing but consolidation apparatus, the test. The clay soil is tested in a consolidometer, showed a reduction in void ratio from 1.83 to 1.51 when the pressure was increased from 145 kPa to 220 kPa. Calculate the coefficient of compressibility and the coefficient of volume compressibility if the soil at site has a thickness of 4 meter. Then determine the consolidation settlement due to the given stress increment. First, you need to calculate the coefficient of compressibility and the coefficient of volume compressibility. It's AV and MV. To do this, very easy. Pressure increase is given and void ratio changes are given. You should be able to do very easy, no? Directly you have to do. That's first you try to do this part. First you do this part. Almost we have come towards the end of today's lesson. Okay, just some two problems like this in the next one. We'll wrap it up. Okay, just try to do this. How to do? How can we do it? It's very simple, right? You should be able to do. So direct, nothing, everything is given. Coefficient of compressibility is AV, right? So 1.82 minus 1.51 divided by, how much is it? How much is it? 4.13 into 10 to the power minus 3 meter square per kilonewton. Right? Next again, MV AV by 1 plus E naught 4.13 plus 3 6 into 3 per kilonewton. Done. So we've already calculated the coefficient of compressibility and the coefficient of volume compressibility. Now we need to find out the consolidation settlement. Right. Now, how to find out the consolidation settlement? Now, CC, we do not need coefficient of compression and all those things. If we can find out MV, if we can find out MV, we can also directly find out the settlement from that, from MV also, using MV also. Is that which using the coefficient of volume compressibility, we can find it. How? You know, delta H by we already did this, right? We already did this exercise. E naught. Now this is equal to SC by H to delta E by 1 plus E naught. Settlement is H into what? Delta E by 1 plus E naught. Now what is MV? MV is AV by 1 plus E naught. So 1 plus E naught I can replace by AV by MB. AV by MB. Right? AV by MB. Or what I can do? No, delta E. Delta E I can replace by AV into delta sigma bar. AV into delta sigma bar. So delta E I can write AV into delta sigma bar by 1 plus E naught. Now AV by 1 plus E naught is what? Nothing but MB. I got H into MV into delta sigma bar. Therefore, this is what? What is H? Given 4 meter thickness, right? 4 meter thickness is given. So 4 meter times MV. MV, how much did you get? 1.46 into 10 to the power minus 3. What is my delta sigma? Delta sigma is 220 minus 145. We get 0.438 meter. Sigma 43.8 centimeter. Okay, so directly from MV we can calculate. So as settlement is equal to H into the thickness of the layer, clay layer, times the MV, coefficient of volume compressibility, times the increase in the effective stress. That gives us the settlement. Okay, that gives us the. Okay. Now let us come to the next. For the footing arrangement shown in the figure, determine the consolidation settlement of the normally consolidated clay layer. Take the unit weight of water as 10 kilonewton per meter. For the footing arrangement shown in the figure, determine the consolidation settlement. Determine the consolidation settlement of the normally consolidated clay. Take the unit weight of water as 10 kilonewton. So here we have an arrangement, right? First, you can see we have a footing. Okay, 1.5 meter by 1.5 meter if you zoom in. Zoom this a bit, huh? I'm putting 1.5 meter by 1.5 meter size square footing we have. And we're applying a load of 4,000 kilonewton on the footing. Okay, the footing is embedded into a sand layer and the saturated unit weight of the sand is 18 kilonewton per meter cube. And you can see the groundwater table coincides with the ground level. The groundwater table coincides with the ground level. The saturated unit. So hence the both sand, the clay are both are saturated. And the saturated unit weight of the sand is given as 18 kilonewton per meter cube. And below we have a clay layer. The clay layer is sandwiched between two sand layers. Obviously, there will be concentration settlement of the clay layer as water will drain out. The application of there will be consolidation, settlement of that layer. Now, first, what we need to do here, similar to the previous problems, we need to calculate the initial effective stress and then the increase in effective stress. The initial effective stress and the increase in effective stress. Initial effective stress, for that I have the unit weight of sand. I will have to calculate the unit weight of clay, the water content, and the specific gravity is given to me. From the water content and specific gravity, I will be able to calculate the unit weight of the clay, the submerged unit weight of the clay. And already I know in the saturated unit weight of the clay, so of the sand, I know the saturated unit weight of the sand. From the saturated unit weight of the sand, I can calculate the submerged unit weight of the sand. I know then I will do the I will be knowing both the submerged unit of the sand and clay. So I will be able to find out the effective stress, initial effective stress at the center of the clay layer. At the mid portion of the clay layer, I will be able to find out the initial effective stress. So generally, what we can do, we generally take at the center of the layer. Otherwise, what we can do, we can divide these clay layers into say several numbers of clay layers, and at the center of each of those layers, I can find out the fish. That will be more accurate. But this process also gives us a good, it gives us the same, almost same value when we have a homogeneous soil. Okay. So generally, we write a computer program to calculate this. So it divides the layer into several number of layers, and then it finds out the we set a tolerance level where if this is greater than this, something like this, then we don't divide it further. Okay, like this. Okay. Simple. Good, we can write. So we need to find the initial effective stress. Then need to find the increase in effective stress due to this loading of 4,000 kilonewton. What is the increase in effective stress at the center of that layer? To this loading of 4,000 kilonewton, what is the increase in effective stress at the center of the layer? That we need to, right? Isn't it? That we need to know. Then what we do, then what we do, then what we do, what how you do. So we consider that the distribution of load from the base of the footing is in a 2:1 arrangement. So you can apply the Bose-Einstein theorem also, and whatever things give that those theorems also you can apply, but the easiest way is that will give you the 2:1 distribution. Okay, 2:1, two horizontal to one vertical. So it distributes in a 2:1 fashion. That way, what I can do, I can find out the stress, increase in effective stresses at this level. And finally, you can use the consolidation, that settlement equation to calculate the settlement. So let us see how we proceed. So first, I have the submerged unit weight of the sand. Right, we know this. So here, 18 minus 10. Then I have to find out the submerged unit weight of clay. Nothing but G minus 1 by 1 plus E, comma W. Will be 2.65 minus 1 by 1 plus E. So what is E? It is not E is nothing but W into G. So W is 0.3143 into G. Right? Times 10. So calculate this. Calculate this. See how much is the submerged unit of the clay. So the submerged unit weight of the clay should be minus 1 plus should be 9 kilonewton per meter cube. Next, as I said, we need to find out the increase in the effective stress. Okay, increase in the effective stress that is coming from this load. Okay, this load. Before that, what we will do, we'll find the initial effective stress. So now initial effective stress. Sorry, yeah. So first you need to find the initial effective. So initial is 7.5 times 8 plus 1.5 times 9. This will come out as how much? 73.5 kilonewton per meter square. Also, we will see CC is given in the question, right? 0.3. Okay, CC is given in the question. Now we have to find out the increase in effective stress. So now increase in effective stress. So if this is 1.55 meter, if I spread it by in 1:2 ratio, 1:2 ratio, this width will be this width, new width will be how much? 1.5 plus 2 into, because this 2 parts here, 2 into, what is the height? What is this height? Z? 2 into Z. So 1.5 plus 2 into 2 into, what is this Z? 7.5 minus 1.5. 7.5 minus 1.5 is 5 minus, so minus 1.5 is 6. So here to here it's 6. And 6 plus 1.5, and again 7.5. 7.5. Right? 3 by 2 is 7.5. So from Z is nothing but 7.5. Right? So 7.5. Okay. So, okay, right? So this is nothing but, okay, this one will get. So what will be the increase in effective stress? 4,000 newtons divided by 1.5 plus 2 into 7.5 square. Right? We'll get this as 4.03 kilonewton per meter square. Okay, so you check all this yourselves. Okay, you check all these problems, check all the answers, all the results yourselves. Okay, do this yourselves once and check the values. Okay, check all the results yourselves. Okay, so how did you get this? Delta A, nothing but Q by B plus twice NZ into L plus twice NZ. Okay, since it is a square here, we are given a square. If it's a rectangle, you can do it like this. If it's a rectangle, you can do it like this. And this is nothing but one vertical is to N horizontal. This is this N slope. Now, one more thing I need. One more thing that I need for the calculation of settlement is the initial void ratio. Initial void ratio I can find out from the CC relation. So CC, so let's see, is it CC is 0.54, E naught minus 0.35. So CC I know 0.54, E naught minus 0.35, equal to 1.05. Okay, now finally I can use my this equation log okay. So it's 3 meter thickness of clay layer. This I got, this is given as 0.38. I got 1.05, right? 0.05 delta sigma. Delta sigma is 0.4.03 plus this initial effective stress, how much? 73.5. 0.8. Okay, so this much is my consultation. Okay, so how did I do this? How did we do this? First we find out the unit weights, then we find out the initial effective stress, right? Initial effective stress. I have the CC with me. Then I find out the increase in effective stress due to the loading that is there. Due to the loading that is there, I calculate the initial effective stress. And after that, after finding the initial effective stress, I find out the E naught value, initial void ratio from this empirical relation with CC. And then finally, I apply this in my settlement equation, HCC by 1 plus E naught log. This is this. And I get my settlement. Okay. So this is what we end today's session here. So this was all the problems that we had to do today. Okay. So we have 10 more minutes in our hand. So Yeah, so I will be here till 6 o'clock. I'm here for 10 more minutes till 6 o'clock. If you have any doubt, please feel free to reach out to me. Feel free to contact me anytime. And now, if you have any doubts till 6, you can ask me. I am here. All right. But our problem session was over, right? Okay. Thank you. And our next session will be after a long gap because there is some readjustment. It will be informed to you in due course of time. Okay, in due course of time, it will be informed to you. The next session hopefully will be on the 10th, sorry, on the 18th of March. Okay, it will be on the 18th of March. Okay, it will be on the 18th of March. So today we had the sixth discussion. Today was the class, the 3rd of March class, and the 24th today's class was done on 21st. And today we did for the 3rd of March class, we did today. And for the later, for the 10th of March session, we will do it on the 18th, and henceforth we'll do. Okay, so we'll meet next on the 18th of March, March Tuesday, 18th of March, Tuesday from 6 p.m. to 8 p.m. Okay, from 6 p.m. to 8 p.m. Tuesday. Okay, we'll meet on 18th of March, Tuesday from 6 p.m. Okay, the class is over. Okay, if you want, you can leave or leave, and if you have any questions, you may please redirect. Okay, I'm here till late. Please feel free to ask, or if you can also leave. All right.